Welcome to the next lecture on inorganic chemistry of life. In the previous lecture, we have looked at some techniques of the spectroscopy and electrochemistry. This is NMR spectroscopy, nuclear magnetic resonance, electron spin resonance spectroscopy, and then also electrochemistry. All of these are extremely useful techniques for studying the reaction dynamics, product formation. All these kinds of things are the enzyme related ones, protein related things as well. Now, let us look at another technique next to that is called the extended X-ray absorption fine structure spectroscopy. Its short form is generally referred as EXAFS, EXAFS. So, extended X-ray absorption fine structure spectroscopy. What is this used for? Why is this used? This is used basically to get in a metalloprotein or a metalloenzyme. There is a metal ion, there are side chains are attached either through O or N or S or a combination of these, that is called primary coordination. So, in order to get the primary coordinated atoms to the metal center, one can use this particular spectroscopy, which is called extended X-ray absorption fine structure spectroscopy. It is the fine structure coming from the X-ray absorption method, and that is what we look at. And we will come to the principle just in a while, and therefore, this is very useful. Another aspect why people use EXAFS, why not crystal structure? We have already talked to you a few lectures prior to this, X-ray crystallography. We talked about different resolutions. You can get the entire protein to a resolution, to a very high resolution as well. But when you have such a thing, why do you want to use this one? For X-ray diffraction, you need a single crystal. For EXAFS data, you do not require a single crystal. The sample can be in the form of a solution, it can be form of a powder, it can be any form. There is no necessity of having a single crystal to be used. So, therefore, in such cases we use extended X-ray absorption fine structure. However, the information is very much limited. So, that means you get primarily the primary coordination sphere, but not entire protein structure, whereas crystallography you get the entire protein structure. That is one difference. But in some cases we require that to know the metal bound region, etc. The second thing is that it is not simple to use this to resolve the fine structure that you got. If you want to interpret in terms of the metal ligand distances and their angles, we need some modal complexes which are very close to that. So, therefore, one needs to study the EXAFS studies even on the modal complexes too. So, require some modal complexes. So, you basically use these modal complexes, study, because in modal complexes already crystal structures are known. Therefore, from that you can try to get the parameters and use those parameters to solve the primary coordination structure in the metalloproteins and metalloenzymes. Initially it has been used quite a lot for the molybdenum case, and later on there are several cases even for iron enzymes as well. Okay, take this, let us look at the principle. Let us take this is the metal center and there are some ligands attached to that, or primary coordination centers. So, when you incident X radiation, obviously we know that the X radiation can knock out even the core electrons. The electron is knocked out, electron will move out of this. So, electron wave of the electron moving out. So, when it moves out, it will start interacting with the electron cloud of the neighbor atoms, which is called the ligating centers. So, therefore, this wave of the electron wave that is coming out of this will interact with the electron cloud of these ones. Therefore, you have some kind of an interference between the incoming or outgoing electron and the neighbor atom electron densities. So, that interference can be constructive, can be destructive. So, when the interference is destructive, you have no peak. When the interference is constructive, you will get a peak. So, this is what you are seeing, peaks that you are seeing. So, that is how one can explain, and of course, this is from the distance from the center of the metal ion. So, you can get, so you get a peak of this kind, and this can be taken in water, any kind of a solutions, not a problem, and can be converted into the distance versus the relative magnitude, relative intensity kind of a plots. Okay. So, to convert those things you require certain parameters, and those coefficients or parameters are obtained by studying for the model molecules. So, for the model molecules you can get all those coefficients, and those coefficients you can use it. Now, here on the right side you have a case or an example where the molybdenum is bound to here tetraoxo, tetrathio and dithiobenzene kind of a complex, or dithiocarbamate kind of a complex. So, you have all these there centers. So, these are all small molecules. So, from the small molecules obviously you can get the corresponding the metal to the ligand distance you can get from this. Okay. So, this is metal oxygen and this is metal sulfur. So, this sulfide kind of thing, then it is a thiolate sulfur, and you know that the metal oxygen when it is single bond versus metal oxygen double bond, you will have a difference between these two. Metal oxygen single bond to metal thio single bond, there will be again a lengthening of the thing, and from a sulfido bond to the metal to the thiolator bond to the metal, again you will have a increase. So, therefore, the bond distances will differ, and from the intensity you can try to quantify how many such atoms are present. So, therefore, by analyzing this entire data, so by analysis you can get the type of primary coordinations, type of the primary coordination bound to metal center, or you can also get the number of such coordination centers. So, essentially you can get coordination number and the metric data from the metal to the ligand distances. So, ML and coordination number. So, these can be obtained ML distances and the coordination number. So, this is what. So, what it constitutes? It constitutes the primary coordination sphere. So, one can resolve the primary coordination sphere using Xray's technique. So, that is to make it simple. I have not taken you to more examples, etc., and it can be studied. All that you require is sample can be in any form, it can be liquid, it can be solution, it can be anything, or it can be put on something else. Anything can be studied. Can be studied in water solutions, etc., but you require some model molecules. So, some model molecules will help you to get these coefficients, and the coefficients will help you to solve this particular spectrum into a useful. Useful means distance relation, distance and intensity, this one. So, you have to convert from this to a distance. So, this is coming from the interference, this is after conversion by using certain kind of a transformation, certain kind of a Fourier transformations, you will get this. So, this is actual spectrum transform, this is the raw data. So, raw information, from this you can get this one. So, let us now look at another technique which is a nuclear technique. So, nuclear transitions. We have looked at nuclear spin transition earlier, electron spin transition, and now we look at the nuclear transition. Okay. So, the nuclear transitions are basically in the gamma radiation. So, they are very high in energy. Nuclear transitions are gamma radiation, so very high energy. So, these are from a nuclear transition. To understand this background for this, you need to understand the, just like electron distribution, nucleon distribution. There is something called nuclear shell model, just like we have the electron shell model, Bohr shell model. So, similarly you have. So, that will talk about the placement of protons, placement of neutrons, etc. But that will be outside the scope of this particular course. So, I am not going into the details of this. Rather, I will try to take you through the utility of this, how one can use it, what is the simple basic the principle associated with it. In the NMR, what have we looked at? We have looked at the chemical shift. So, in the mass buoyer, what you will see equivalent to that chemical shift is called the isomer shift. So, this is referred as the isomer shift. So, what is this isomer shift and how does it come? Isomer shift, suppose you take the nuclei should have a I value first of all in order to study the mass buoyer, and most commonly studied is the iron. So, iron and iron complexes, iron proteins, etc. Iron containing proteins, all of these are well studied. You can study many other nuclei, but not so much of important. Iodine can also be studied. So, you can study for iodine, and you have many other things like silver, platinum, many cases you can study the corresponding. So, isomer shift is when you take simple iron metal versus your iron complex, what will be the difference between these two, and that is what you study essentially to get the isomer shift. You need to prepare a gamma radiation, that is which is called the emitter nucleus, and this is your compound where it will absorb. So, absorber. So, this gamma radiation is absorbed. Okay. So, as a result of that you get the corresponding peak is coming in. So, this peak is shown as the percent of transmission versus that of the isomer shift. Isomer shift with respect to the standard. So, in case of iron compounds, iron 0 is the standard. So, in case of iron complexes, Fe metal or Fe 0 is the standard. So, with respect to that, you can define the isomer shift. With respect to that, you can define the isomer shift. Now, so there are other things which are, so in case of these complexes will have some kind of a symmetry, asymmetric kind of a geometry. So, such kind of geometries will further split this particular bands into more than one. So, you can see there are two peaks are coming out of the one, that is what is called the quadrupolar coupling or quadrupolar shift that comes into these ones, because the nuclei having the quadrupolar system. So, therefore, quadrupolar nuclei means greater than 1, I is equal to greater than 1. So, this is quadrupolar nuclei will couple with this transition and give the splitting, and that gives the quadrupolar splitting. So, what you are finding in this is quadrupolar splitting, and this is referred simply as QS. Okay. How does one do this one basically? So, you have a gamma radiation coming out from the emitter, and you have a sample is put on a rails. Therefore, you can move the sample either towards the radiation, away from the radiation. So, to adjust to get the resonance, so to get the transition. So, therefore, if this is a source and if this is a source which is giving gamma radiation, if this is sample and the sample is put on top of rails and then you try to move the sample towards and away, towards and away. So, with this particular thing you can get the transition. So, where at a particular stage you get a transition, and that is what the value of isomer shift is. So, the isomer shift will come, and this basic shift is compared with respect to the iron 0 kind of thing. Okay. So, here with no isomer shift, so you have the plus half and plus 3/2, and when you have the quadrupolar splitting, then you can get further split of these ones. So, you have the transitions going 1 and then going 2, and these 2 transitions are seen over there. Okay. So, therefore, similarly various cases here, even if this half splits further into plus half minus half and 3/2 shifts splits into plus 3/2 plus half minus 3/2. So, therefore, you have a transitions taking place. Therefore, you get correspondingly all these bands. So, these ones can be seen over there. So, and this is also influenced by the kind of a geometry or symmetry you have with respect to the metal center, because metal center is a coordinated metal center, primary coordinated metal center. Therefore, that will be dependent on these ones. Okay. So, let us get bit more how do we utilize this data, information, etc. So, for example, you know ion complexes. So, in the case of ion complexes, the ion center will have the iron center. So, will have iron 2 plus or iron 3 plus, and each one of these can be either in low spin or high spin. And similarly, iron 3 plus can also be in low spin and high spin. And in case of ions, you even get intermediate spin too. So, I would like to inform you one of the most important techniques that can differentiate iron 2 plus, whether it is in a ferrous, whether it is a ferric, and whether it is in a high spin or a low spin. So, ferrous ferric 2 forms, high spin low spin 2 forms, 2 into 2 4 different forms. In fact, in addition, the iron case you also get some intermediate spins too. So, more than 4 forms. All of these can be very well identified when you study Moss biospectroscopy. No other method will give a full resolution of this low spin, high spin versus the iron 2 plus, iron 3 plus. Even if you study the magnetic part, you need to study the EPR. All of this can not give full unambiguous way of identifying whether the ion center is in ferrous form or ferric form, 2 plus form or 3 plus form, whether the ion center is in the low spin, whether the ion center is in the high spin. The only technique that you have is the Moss biospectroscopy. So, from the isomer shift, you can talk about this whether it is in the iron 2 plus, iron 3 plus, and from the quadrupolar splitting you can get whether it is in the low spin, whether in the high spin. All of these can be identified. So, the iron 2s will have a different kind of a lines, iron 3 will have a different kind of things, then low spin will have a different, high spin will have different. For all of these, the geometry of the primary coordination sphere will also play a role. So, I think I will leave that Moss-Boyer technique at that particular stage and then go to another technique which can be used very easily. One can use it very simply. In almost every research lab you will have absorption spectrometer. Therefore, studying the absorption spectroscopy of the protein ligand interactions, protein substrate interaction, substrate converting into the product, all of these can be studied by absorption spectroscopy. So, absorption spectroscopy in this, the ground state electrons are excited to the excited state by the absorption of energy, primarily either in the ultraviolet region or in the visible region, depending upon the type of electron or nature of the electron that you are talking about. Okay. So, that is very well known. Most of the transition simple organic molecules are in the UV region or slightly shifted when you have a lot of conjugation into the visible region. Is that in case of inorganic chemistry or inorganic complexes or inorganic proteins, or in other words metalloproteins, when we want to look at, we need to understand the following things. Now, let us take two of the geometries, two of the most popular geometries are the complexes, the octahedral and tetrahedral. And octahedral and tetrahedral, without going into more details, I would like to tell you the following things. You know, the intensity or absorption of these is dependent on the epsilon is absorbance of these. So, absorbance of light, to what extent it absorbs, this depends on epsilon, depends on C and L. C is concentration and L is path length, and this is the absorption coefficient. This depends on the power of absorption of that particular group in that particular molecule. How good, how strong, how weak it can absorb the light of that particular wavelength. Okay. So, this is the basically absorption coefficient, and for every group at any given epsilon, it will never be absorbing in the same level. Some of them will be absorbing very strongly, some other groups will be absorbing weakly, some other groups may not absorb at all at that particular wavelength. That means their epsilon will differ. If by keeping the concentration constant, path length constant, you can basically look at the absorption levels or absorbance, all molar absorption coefficients. So, these kind of a molar absorption coefficients can be compared. Now, let us come most common geometries are octahedral geometry and tetrahedral geometry. For reasons that I am not explaining here, in case of in both the cases we are talking about the d transitions, or we can talk about the other transitions as well, charge transfer transitions also. So, these are the transitions that we look at. Now, you look at this particular plot, it shows the what is plotted here is a molar absorbance or epsilon molar. On this side, this is meant for the octahedral, and on this side it is meant for the tetrahedral. So, what do you see in this? The tetrahedral ones, molar absorption is 100 to 700, and for the octahedral complexes something like 0 to 12 or 14 or something, or let us say 0 to 10 and 0 to 600. So, therefore, there is a increase of 50 to 60 fold absorption level of increase by tetrahedral complexes. Now, if you take a protein, let us say you take a metalloprotein and remove the metal ion, so it will be apoprotein. So, you take an apoprotein and you start adding the take apoprotein and add metal ion. So, you start forming a metalloprotein. So, you can measure the absorption spectrum as a function of addition of the concentration of the metal ion, etc. So, you will get more and more, and from that we can calculate the absorbance levels and epsilon values. Everything is possible for that. From that epsilon, you can get whether the epsilon range is in the very small value, molar epsilon, or is a large value. From that you can identify the ion that you added, so metalloprotein, whether this is tetrahedral or octahedral. So, that core, the primary coordination core can be can be determined. So, that is very interesting. So, you take the metalloprotein, remove the metal ion, start adding the metal ion to that, you can titrate that too. So, it is a boon in disguise. They have a different absorption capabilities, the capability with the lower, with the higher, and the reasons are there which will be explained in spectroscopy course and based on the inorganic chemistry courses, but I will not go into the details of that, because some of the transitions are allowed, some of the transitions are forbidden, all those kinds of things come into picture, which I am not explaining you. All that I wanted you to see, that appreciate that these DD transitions, the DD transitions are very strong in tetrahedral, at least 50 to 60 fold or even 100 fold stronger in tetrahedral, and they are very weak in octahedral. Reasons I am not explaining for you. Now take some example case here, over here, and you take digly is a peptide. You take the digly and add the copper salt. So, as you keep adding more and more copper salt, copper 2 halide or something, you can study the absorption spectra. Now, you can also make, of course, a complex with it and change the pH of the solution too. What will happen when you go from here, the initially formed complex, okay, which is in the form of carbonyl and carboxylate. Now, when you increase the pH to somewhat greater, then the amine is binding, the nitrogen here, the amine nitrogen is binding, carboxylate binding. So, the binding modes will change because this pH will change the pKa characteristics of the corresponding groups. Therefore, some of these groups become, so this is as it is, and this nitrogen will go into binding form. So, this nitrogen will go into binding form, the carbonyl will go out of this. So, that means at different pHs, if you do a pH titration and then plot the absorption spectra, you can see here, you can see that between the 600 and 650, and you also have at 550, all of these, both the DD transitions as well as the charge transfer transitions are changing. Now, if you take this intensity is epsilons, molar extended coefficient, and plot as a function of pH, you get a sigmoidal curve. You see that sigmoidal curve. If you take a derivative of this, you will get the peak position. If you derivatize this one, or take somewhere center point of it, the center point will give you the pKa for this particular protein. If you have more than one pKa, there will be two curves will be sigmoidal curve, more than 2 it will be 3 sigmoidal curve. Okay. So, it will be like this. So, therefore, you can get any number of pKa's that are present. So, therefore, you have pH versus epsilon, and then if it goes, okay, and in some case here you have only one, and then pH versus epsilon, then you may have etc., etc. So, you will have one pKa here, pKa 1, pKa 2, etc. So, you can have that too. So, different pKa's of the protein can be established by using this one, and you can establish the octahedral, tetrahedral. So, therefore, quite a well things. Now, suppose you are doing a reaction with the substrate may displace some other things, the geometry will change, therefore, your absorption spectrum will change. Now, the substrate binds, again the geometry will be refilled, again you can study that as well. So, therefore, there are various methods of spectroscopy, various methods of microscopy, crystallography, X-ray diffraction, exhaust. So many techniques can be used to establish the protein dynamics, protein conformation, protein substrate interactions, substrate conversion to product, all of these kind of things. So, in effect, what I would like to say is, let us recapitulate what all I have talked about is, till now I have talked about the how one visualize the metalloprotein. A metal ion plus protein surrounding is like a coordination complex. Metalloenzyme, metal ion plus protein surrounding plus function. So, I also explained to you in the beginning what does the elements do in biological system, which of these elements in the periodic table and why, how are these elements absorbed, what concentrations, what will happen when the concentration is changed, I explained to you this deficient and excess syndromes, all of these. And so, what are the various ways by which these ions are bound? They can be bound directly to the protein side chain, they can be bound through special units like porphyrins, etc., and then in turn they are bound. Then after that I explained to you general perspectives of proteins, nucleic acids, mutagenesis, and lately in the last 3 lectures or so I have tried to cover the techniques of the biological inorganic chemistry like spectroscopy, microscopy, crystallography, etc. Prior to that I have also explained to you coordination chemistry principles. So, this will bring to a kind of a conclusion of the overall integrated introductory approach to this particular course of introducing metal ions and the inorganic chemistry of life. In that inorganic chemistry of life, these are all very introductory, and these introductory things are useful both for the bachelor student as well as master students who will be continuing the course further. Thank you very much.